Okay, we're going to start some Chapter 17 in a second, do some Chapter 17 homework. Let's see if we got anyone in the chat. I need to wake up Mewbot again. Mewbot is going to be here in the chat. Gonna get some music going while we get the chat going. Where is it? No! I can't believe the week's almost over. I can't believe it. Getting my Pearson up. Here's the live stream. Hey, I see someone in the chat. Darius, what's up, Darius? How you doing? Darius, let's throw you some Mewbot points. You ready to do Chapter 17, Darius? Got the chat up and going. Sorry for the delay. I went on a walk. It was such a nice day. A little bit of rain, but such a nice day. And there were so many students. They're doing a bunch of stuff, like doing a marketing class and everything. Got to point out where I'm from, New York, and a lot of fun stuff. Got to see a bunch of dogs. So many dogs. So just great stuff right there. So huge shout outs. A lot of fun. And then you got the free food truck, right? I went out and saw it. I ate my sandwich. I got my sandwich. It's crazy being a germaphobe. Can't eat all the free food sometimes. You're like, meh. Anxiety. We all have our own struggles. So let's go in here. But it looked really cool. And shout outs to them for doing it. Shout outs to them for having a free food truck. That's really awesome. Okay, we're going to start up. Whoops, clicking every button at one time. It's not a good idea. Let's go get some homework done. Let's do it. Okay, so this is Chapter 17. Let me put it in the notes. Same. Yeah, I had the tree truck. Nice, that's awesome. Man, man, now I want the nachos. Man, nachos are so good. Nachos are good stuff. Was it Ron Stoppable ate nachos? Like impossible. So we are doing a Stat 201, Chapter 17 homework. Question 1. Do customers spend more at Walmart or Target? Now, when you do problems, you want to think about the steps to solve these problems. I'm actually going to take and transfer something right here. Let me see. I'll show Charlie that other thing. I'll take another screenshot. Okay, so when you solve a problem like this, you have to think about the steps you're doing to solve it. The first step when doing hypothesis testing, which it doesn't ask us to do, but it's good knowledge, is to write the null and the alternative. The null hypothesis would be that the average amount spent at Walmart, and you could do minus Target, but you could just say that they are equal to the average amount spent at Target. It doesn't specify, I think, whether it's a positive or negative difference. We might just say the alternative without specification is that the average amount spent at Walmart, that stands for the true mean amount spent at Walmart. Mu is true mean. Like, for everybody who goes to Walmart, the true average is not equal to the true mean of Target. And so that's what we would see right there, that the true difference is that they're not the same. That is the alternative. It doesn't ask us that, but let's look what it says. To perform an inference on the two-sample T, what conditions must be met? Darius, what's condition 1? Condition 1. My voice cracks. Condition 1. Random. We know randomness right there. So we've got the conditions. We run through them a good bit in lecture, and they're listed right here explicitly. We pause when we get to the third and fourth because it can sometimes change, and because we're doing quantitative, it will be nearly normal, meaning the distributions are basically normal. Can be checked with the large enough n condition with the central limit theorem, and we have the independent groups condition. And we went into a little more detail down here. I found another portion in the notes where I could also write it out a little bit more. And I thought I did it right. Oh, there we go. There's the ways of checking it. I thought I wrote it out a little bit more. Hey, Dylan, good to see you. We're doing the homework right now. Just talking over the conditions. Let's see which of these makes sense right here for the conditions. So what conditions make sense? One must assume... kind of right. But one must assume the samples were randomly sampled. It must also be assumed that the distributions are nearly normal. It kind of says nearly normal. It'd be a good idea to make histograms to check this. That sounds right to me. Yeah. So the first condition is randomly select them, which also deals with independence. If things are randomly selected, they'll be independent of each other. The next condition is less than 10% of the population is selected, which we're only talking to 83 and 85 customers. So we probably talked to less than 10% of total Walmart Target shoppers because there's a lot. And then the third condition is we'd have to look at some sort of histograms or something to assume that the distributions are nearly normal. And the fourth condition is the independent means. The mean for Walmart would not impact the mean for Target. And those are probably independent means. That's first question done. See, it doesn't go enough in depth. That's such a very easy, quick question. I mean, we already got a 15 or 14% on the assignment. So we're 1/7 done. Let's go right here and do 552. One question done. Let's do the second one. Sports reporter is analyzing who's older, professional baseball players or professional football players. So with this, you think about what the null hypothesis would be. This is just practice for us right here to know the null hypothesis. The null hypothesis, when you test the difference between means, is going to analyze the difference between a football player and a baseball player and analyze the true difference and assume that it's equal to 0. And that is the null hypothesis. Unless otherwise stated, we will assume that the alternative... Did I seriously just go off the screen? Because it won't let me do it off screen. The alternative hypothesis is that the difference is not equal to 0. The true difference between the average age of a football player and baseball player is not equal to 0. And with this, what are the conditions? Well, it's kind of a repeat question. Conditions are random, 10%, and then we pause to make sure we're choosing the right conditions. I want to show you something right here quick. I have a video under Review 3, so click this right now. Get ready because you're going to need it for later. Review 3 on the Stats 101 page has all the review videos on how to do a lot of the tests and the hypothesis and the intervals and all that good stuff. And if you go down here at the very bottom, you will see videos from December. It's like November of... When did I do it? December 2019. 5.5 years old videos, or 6.5 years, something. It's pretty old. There's little baby Brian. Look at that. He was so much younger back in the day. And you can see all the conditions right there listed out for you. Very important. You can see random, 10%. And then when you get down to the next condition, whether we're doing success failure for categorical data, that's when you're doing like a 1 proportion confidence interval, 1 proportion z-test, or you're doing the means where you're doing a 1 sample t-test or 1 sample t-interval, 2 sample t-test, 2 sample t-interval, or doing the chi-square test of independence, which is chapter 19. We'll get there soon. So we're doing the nearly normal independent means. Make sure you know this. Make sure to write it down. And that gives us the right answer for the question. So clearly, we want to see that our samples were randomly selected. And it must be assumed that distributions are roughly normal. We could also check that the means are independent of each other and all that good jazz. Well, Darius, we're going to have this done pretty soon, aren't we? We're just flying through this. Any questions right now? I'm trying to throw in new things to be like, and did you know this? Do you know the other conditions? I know. Let's do it. Tell people just join in. We'll get it done. Okay, so this one right here, you are taking some popcorn bags and you're laying them on the counter or putting them in the freezer overnight. Then you're popping the popcorn bags as a class and you're seeing which popcorn bags pop more kernels. Now, we are doing the math freezer minus counter, which is very important because it could be on average. I'm trying to figure this out in my head. I'm going to make this -33. Much better. Much better. Cool. It could be on average that this one had, let's say, 125 unpopped kernels, and this one had 50 unpopped kernels. So what was the observed difference between them? What was the observed difference between them? So do you see this right here? What is the observed difference where the counter had 125? I'm making up these numbers for a point of working with this. And the freezer had 50 unpopped kernels on average. Like a bunch of people went to their counters and left the popcorn bags on there and then popped them overnight. And then a bunch of people went to their freezers and put the popcorn bags in the freezer and then popped them overnight. So there's a difference of 75, right? The counter had 75 more unpopped popcorn kernels. Now, why do we not see 75 over here? It's because -75 is the what of the true amount of difference. -75 is our what of the difference. We put it way earlier in the notes today. -75 is our what of the true difference. I swear I wrote it down. There it is. Oh, Dylan, fire. You got it. It's the estimate of the true difference. That's what we just did right here. It's the estimate of the true difference. So we have to give a margin of error. Really good question right here. So this is the estimate. What is the margin of error if you look back up at this interval? So this is just good practice and good estimates right here. What is the margin of error if you look at the interval? Like we think the the counter method has about 75 unpopped popcorn kernels more, plus or minus what? So you have to look back up here at this. So now you have to know how to get a margin of error from that. If you don't know, say don't know, but let's see if you can get it. I'm trying to come up with as many questions from these as I can to see if you can get them. So here's the way it looks visually. You ready? 75 or negative 75 is the estimate at the center of the interval. A margin of error is half the length of the interval and is the plus or minus. The numbers you see here on the interval are the lower and the upper. So the lower value is negative 117 and the upper value is negative 33. So what is the margin of error? Remember, the margin of error is a plus or minus, so you want to do minus the margin of error and plus the margin of error. This is the estimate. So the estimate minus the margin of error is the lower, so estimate minus margin of error equals lower. And the lower value is this. Do that. All you're doing is looking at how far these things are away. So what's the margin of error? I changed the number to make it easier in the problem. Who knows the margin of error? Margin of error is half the length of the interval. I think it is 42. Nice job, Dylan. And then you can check your work right here by just plugging in the numbers and making sure you get those. You can also do the following. If an interval goes from like 30 to 50, very quickly, what's the margin of error for this? If an interval goes from 30 to 50, what's the margin of error? And then you'll realize the margin of error is half the length of the interval. If an interval goes from 30 to 50, the margin of error, well, that's the whole length, Dylan. Good work. That's the full length of the interval. The margin of error will be 40 plus or minus 10. So the margin of error is always half the length of the interval. So the full length of the interval would be 20 because you'd go right here and you would draw 40 in the center and then 30, 50 plus 10. Does that make sense right there? It's easier when they don't have decimals. Who feels like they can see it now? Be like, oh, the margin of error is like half the length of the interval. You can do the center. Well, the median isn't actually it is. It technically is. It's the average of the median. You can find it mathematically by finding the middle number between them. You can just average them. So the center of the interval is the average of the upper and the lower. You can do 30 plus 50 divided by 2 equals 40. So you can average the numbers, or if you subtract them and get their difference, you will find the margin of error if you take half the length. So 30 minus 50 divided by 2, half the length of the interval will get you 10 or negative 10, but you just plus or minus 10. Does that make sense? The margin of error is half the length of the interval. The center of the interval is the average of the two numbers, which is the estimate from the upper to lower. Since both numbers are negative, the counter had more unpopped corners. So the counter is larger than the freezer. Yeah, should be right. That was easy. Okay, just good review. A lot of people don't realize how to do those on the test. I've had people be like, wait, how do we solve this? Like, margin of error is half the length of the interval. That's all it is. Once you know it, you're like, oh, I get it. I know it. I can do it. In order to use the methods in this chapter to compare two means, which of the following is not a condition? Help me out right here. A, B, C, D. If you watched the video from earlier, is it A, B, C, or D? Which is not a condition right here? For the chapter on the means, Mr. T, there should be two you go through pretty quickly. It's A. Because whenever we do the test for the mirror chapter, random, always there. 10%, always there, as in less than 10% of the population sampled. And then the third condition is nearly normal. Not listed, but it is a condition. The fourth condition is independent means, and success failure is used for categorical data. We're not doing a categorical Y of interest right here, so it's only used for categorical data right there. And nearly normal. Exactly, proportions, which are categorical. Darius, points right there. So proportions, categorical right there. Okay. Only a few more. I like it. Boom. Nice and easy. And the important thing is not just to solve these. And great job, Darius, and also Dylan. It's to know the why behind them. So you have to understand the why so you can solve any problem. So this company is running a statistical test, and they found a p-value of 0.124. What does that instantaneously tell you? Just when you hear p-value of 0.124, what should you think? You see p-value 0.124. What does that mean? What does that mean? They found a p-value of 0.124. You should know, like, oh, that means this. Huge thing you should know from this class. Their results were what? Given an alpha of 0.05. Given the alpha, which we traditionally use of 0.05, their results were what? Not significant, exactly. So statistically significant means p-value less than alpha, which is 0.05 unless otherwise stated. So they were not significant. So now let's think about what they were running right here. What they were running is they were running a test to compare the beef and the meat hot dogs and look at their difference. So they were using the null hypothesis of mu meat minus mu beef equals 0. And they're looking at the calories. So what does this question? It's saying the average calories of a meat hot dog, which I guess is just meat, I don't know what it is what to a beef hot dog, especially if we think of it this way. What does the null believe? The null believes that what? Explain to me in words what this means. What does that even mean? It says true mean calories of meat equals true mean calories of beef. What does that mean? What do you believe currently? What is the current belief unless we have evidence elsewise? It also means true mean of meat minus true. Like, if we had all the meat hot dogs in the world, tell me in your own words. I'm going to tell you my words. If we had all the meat hot dogs in the world and all the beef hot dogs in the world, we measured all the calories of all the hot dogs, what? They're equal. Yeah, good to see you there. 5,000 points. Yeah, that's it. It's that they're equal. It means there's no difference. It means the difference is 0. Now, what did we do to this null? When the p-value is low, reject the null. When the p-value is high, da-da-da-da. What are we doing to the null right now? Because we say when the p-value is low, p-value low, reject the null. When the p-value is high, what do we do? When the p-value is low, reject the null. When the p-value is high, just let it fly, let it be. So this is do not reject. Classical sense, fail to reject. Do not reject. So think about this. If we're not rejecting the null, we still believe it. Does that mean 0 is plausible or not plausible? Does that mean 0 is plausible or not plausible? If we don't reject it, fail to reject. If we don't reject it, 0 is plausible. Like, I look at 0 and I say, I don't reject that. Is it plausible? It's plausible. Great job, Tamara, right there. So what does that mean in an interval? The interval we would have created would be something like -8. We're trying to estimate the difference, remember? I'll change color here. Change color. -8 through 4. So I think it could be the case that maybe beef, I'm just making this up for example purposes, beef could have up to 8 calories more, or it could be the case that meat has up to 8 calories more. What do you notice about this interval? Because 0 is plausible, what do you notice about this interval? This interval would what? Which is a lot of times what my Pearson's going to say here. Since we didn't reject 0, the confidence interval must logically what? Because we're not rejecting 0 in our test, so the confidence interval would logically what? As you can see right here, it must what? The confidence interval would logically, think of a C word. The confidence interval would logically what? It would logically what? So the p-value is high, meaning we'd lack evidence. So 0 is a plausible value for the confidence interval. So would it be in there? It would include, it would contain 0. So it would include it. It's a plausible value of the truth. It's a good question. It's a little quick, but it's a good question. For the t-test and t-interval, go here. Oh no, I did exclamation only. This is where people are going to get stuck on question 6. They're going to say, I have no clue how to do this. It's a multi-part question. Theory questions are done for the moment. Easy questions over. Okay, so let's do it. Question 6. With this question right here, it literally just jumps you into the deep end. It says make a 95% confidence interval. What do we need to do for a question like this? Leo knows. Leo always knows. We need to start with what? I'm going to have you help me out with this one. What do we got to do? How are we going to solve it? You get to a question like this that asks you to solve. What do? It's a man riding routes, 2 different routes, route A, route B. We got to do our notation. So when we make a confidence interval for the mean, which is on the formula sheet for the test, it's y bar, and they want to do b first, just the ordering of it right there. Y bar b. This is the true, like if he knew for the truth of the difference between the routes, which he doesn't know, he only has an estimate. Y bar b minus y bar a, plus or minus, which is the margin of error, the t with degrees of freedom from the complicated formula, star because we pick it based on the confidence level, so that's related to the 94% confidence, square root, which is this full thing is the margin of error, s sub 1 squared over n sub 1, s plus s sub 2 squared over n sub 2. Tell me any of these numbers in the chat. Any of them. If you read it, Route A had an average of 5 miles. And, oh wait, he wants to see if it has a difference of 5. That is the hypothesize that he's checking for. Each day he flips a coin to see which way he's going. Y bar B, 50 minutes. Nice job. Let's check it. Y bar B. So the average of B was 50 minutes. There we go. Anything else? Y bar, man, on fire, Dylan. Dylan's already just got it, Dylan. Nice job. Now look at that. That's a difference of 2 right there. So this actually, if you plug in 50 minus 48, it's a difference of 2. And so we already got what the estimated difference is. We'll worry about the t here in a moment. Anything else? I'm going to run out of color. S sub 1 is the standard deviation of one of them. We can just pick one. You can't mix these up. There's the standard deviation of 1. And he wrote each route 20 times. So that's actually the same sample size. So that'll be 20. And then the other one has standard deviation of 5. We have just enough color here. Here we'll do this. That one has a standard deviation of 5. And yeah, it's going to be horrible. There we go. The T, great job, Vienna, too. The T is kind of the more painful thing to get. It's not too painful. We have to do the following. You have to go to the T applet. And on the T applet, you need to enter in the following. You need to go to Welch's degrees of freedom calculator. That's the 2 sample T degrees of freedom. And we're going to enter in the standard deviation of 5 and the standard deviation of 2, because these are the standard deviations. Sample size of 20, sample size of 20. There are 24.93 degrees of freedom. Now we go back to calculate the T that we're going to use using the percent p-value. We enter the degrees of freedom. We go to 4 decimal places to make sure we get it. And there is the T when we click between. Make sure you've clicked between. 2.06 should do. It rounds close enough. 2.06 should be good enough. Make sure you have the right degrees of freedom, calculated from the Welch's degrees of freedom. And then make sure you've clicked between, which I almost didn't click. And then make sure you have the right percent confidence. So there's 3 things to check right here. 1, you need to have the right degrees of freedom. Make sure to calculate that via the Welch's degrees of freedom for the 2 sample T. Next, you need to click between because we're doing confidence intervals. Greater than test, less than test, not equals to test, confidence interval. Next, make sure you have the right confidence level. We're making the 95% confidence interval. So that's the right T, 2.06. 2.06. 2.06. And we just start solving. Like from here, this problem is just plug and chug. It's just like not that bad. Can I get it? Let me see here. I'm looking at it. 429. That's a tricky one. Tricky. Maybe. Okay, let's see if I can get it. This is my guess. 2 decimals. Let's see how close I was. Okay, solving the exact math right here. Let's figure out the standard error. The standard error is going to be 2 squared, which is 4, plus 5 squared, which is 25. So it's going to be 29 over 20. There's that, square root. And that's where I made my error. So actually I can take a better guess right now, and I can kind of get it. So this should be right. Nope. Okay, just ignore me. Let's actually solve it. So the standard error is 1.204. That's the standard error. That's the last quantity there. The T is 2.06. The estimate is 2 plus or minus. Now that's the margin of error. So we take right here 2.06. Maybe that's the issue. It's going to be a little bigger than I thought. I'm very close. So it's 2.48. Well, that tells me the answer. I know I've said that multiple times right now, but I couldn't be more sure until I'm not. It was 2.48, was it? Because I just found the margin of error. So I was getting closer. I had some good guesses right there. Solving out the rest of this mathematics, it's 2.48. So it's 2 plus or minus 2.48, which is a lower bound of negative 0.48 and an upper bound of 4.48. So who follows this? Did anyone else was anyone else able to solve theirs? You just have to plug in the numbers. You take all the numbers and plug them in verbatim. Make sure you can find them. If you plug them in, the hardest part for people is the t. People just get stuck on finding that. It's probably going to be close to about 2.5, 2.05 or 2.06. If you have smaller sample sizes, like if this doesn't say 20, it's going to be a bigger t, like 2.14 or something. Like if I had sample sizes of 10, with sample sizes of 10, it'd be different. Can you show how to do this? Yeah. So you got to put in each of these right here, Dylan. You have to put in your standard deviations. Does this make sense, Dylan? You have to put in your standard deviations and sample sizes. And then once you put in your standard deviation and sample sizes, you then take the degrees of freedom, like this is pretend. Once you get your degrees of freedom, you go to find the t using the p, which is going to be the probability. We're going to do the 95% between. You make sure to put right there. So once again, if you have a smaller sample size, it's going to be a bigger t statistic because it's less like the normal. So you have to have the right degrees of freedom via the Welch's degrees of freedom calculator, found right down there. And then you have to put the degrees of freedom here. Make sure you have the right confidence, which it's 95 by default, so you should be good on that. And then you have to click between. Make sure you're not on the other things. Between is a confidence interval calculator. Is that how you doing, Dylan? Let me know. The people get stuck on the T on this. Everything else is just marking where the standard deviations are, marking everything. It's just if you find all the notation for it, you're good to go. But the T is where people get stuck. And then you just plug the numbers in and make sure to solve math correctly. Good stuff. Let's see right here. Should he believe the claim that you'll save 5 minutes? No, it's not in the interval. Don't believe it, things that are outside the interval, because the interval does not contain it. So you'd reject that at the 0.05 level of significance on the two-tailed test. This one, this one is harder because of all the math. It's just big numbers. But you know what they gave you to start? They gave you the degrees of freedom. So you can just go straight to the applet and find the t. So we're going to enter in 100. You can enter in 100. You can throw the decimals on there. And there's the t, 1.984. We'll do the extra 1.984 because we're working with decimals. And we already found the t. Oh, I got to mark this. 1.984. Okay, let's mark it in the notes. And we should do the children's cereal one. That one gets people stuck. Okay. I marked this. Let me mark this a little bit backwards here. Cool. Okie dokie. So we already found the t. Check out where we just did that. The t was equal to a t with 95% confidence. It is 95, right? Oh, no. Am I right or wrong right now with my t? Am I right or wrong? Say right or wrong in the chat. I think it's 1.984. It's going to be more. I'm wrong. It's going to be like 1 point right there. I'm wrong. I get it. I'm wrong. I asked. Excuse me. It's going to be about 1.6. I think you did. 1.682. Let's see. All I'm going to change is what right here? Watch it. Right here. 1.66. Who's done that? 1.602. I was 1.66. Very close. She was 1.66. I could have guessed that. There you go. The next fourth decimal won't really matter that much. That's the t with 90% confidence with about 100 degrees of freedom. So everything right here relates to the t, the confidence level, and the degrees of freedom. Both those has to be used, and you have to click the between button because you're doing a confidence interval right there. It is not 1.984. That is for the 95% confident. It is 1.6604. So there is our t, and we literally are just taking this formula right here. I think it says we're supposed to do waterfront minus non-waterfront, so it's mean of waterfront minus mean of not waterfront. That's a N right there. I can't spell. Not waterfront. And then plus or minus, which is the margin of error, the t that we just found. So it's a t star with complicated formula degrees of freedom. My pen's acting weird. Square root. And then we go here, s sub 1 squared. Doesn't matter which one we put. You could, sure, waterfront. Waterfront squared over n sub waterfront squared plus s sub. Since you're adding these together and addition works, that you can do either which way of addition. You can call it 1 or 2. You just make sure to do both. And how are we doing in the chat? Is this making sense? We're literally just going to plug in numbers right here. So you're going to take all your numbers over there and just plug them in. It's a bit of a mess because the numbers are bigger. So that's where it gets painful. Yeah, you just plug in the numbers. I don't find this chapter to be that bad. Oh, don't square that n. That n is not squared. The s's are squared up top. The n's are not squared. And so the waterfront was 314.542.35. We're going to write this a little bit lower here. The non-waterfront was 21646.0.51. We're just replicating that number right there. And the t statistic is 1.66. The s for one of them is 98021.97. The other s is 146,595.29. The sample sizes are 110. It doesn't matter if you put the two together correctly. Make sure you do that. And make sure to not put a wrong number. I've done this problem many times and just thrown a wrong number in the wrong spot. You've got to make sure your means go over here, your standard deviations go up top, and they're paired with the respective right sample size, hence why this one is paired with this one right there. So just make sure to grab the right numbers. And now you just solve. I usually start when I'm solving these by going through, we'll do it up top. When I'm solving these, I usually get the standard error first. So I'm just going to solve this whole quantity over here. And 98021.97 squared. And then we're going to divide by 110. That is that quantity. I'm copying it into my calculator, so it's copied right now. And then we take 146,595.29, square it, and then we divide by the 66. And then we're adding this. That seems right. Then we're adding this to the other quantity. And then we're square rooting it. So we have just found the standard error. 20,321,34. So 20,321,34. I think that's right. And 1.66 is still there. We have to multiply those. Now we have to find the difference. The difference is going to be the first part of the interval. Actually, let's just times this by 1.66 so we have all the decimals. There we go. 337,3343. That's the margin of error. 3373343. Is that it? It's interesting. It's palindromic right there. It is. 07. And now let's find the difference, which is this component over here at the start of the interval. It's everything before the plus or minus. We're just subtracting the two means. 314,542.35 minus 216,460.51. Calculator errors are what's going to get you here. 98,001. 98,081.47. I didn't say it to myself, so I just saw it. 8184. Okay. And so really it's just this component here. We're just going to add these two numbers. It's the same thing. I just didn't solve it up top. It's multiplied for the margin of error down below. That's the t statistic, which is the critical value. This is the standard error. That's the standard error right there. Multiplied together, they make the margin of error. That's the estimate right there from those two values. It's kind of important you know where these components are, that this is the estimate. It's the same thing as that. The critical value is part of the margin of error. Margin of error is everything after the plus or minus right there. So the t component is part of that, and it's part of it. The other component of the margin of error is going to be the standard error. So the standard error is everything over here is the standard error. That's the standard error. Oh, I highlighted it the same as the difference. So just making sure you know what is what. The standard error, let me get a different color here. That's the standard error. So make sure you know those components, that the interval is y bar minus y bar 2 plus or minus, which is the margin error, t times the standard error of the diff. So real quick abbreviation of it. Okay, well, we just add and subtract the number there. So there's that number. And we just go plus 3373343. And we go back over here. We're just adding it. So the higher number is this. And then minus 3373343. We're back at the center. We're not. What? Yeah, it's so easy to calculate this one wrong. Oh, I seem to have plussed it twice. So let's go back over here. The upper looks correct. And now we need to go look at the lower again. The lower, we can just take 98081.84 minus 3373343. And there's the lower. Oh, maybe I did it correct somehow, magically. I don't know. And round to the nearest whole number as needed. Really? You don't like decimals now? Really? Really? Woo! Using two calculators right there. I don't think our hundreds of millions. Your prize worth $200 million. You know what's so funny? It's like question is so old. If you could find waterfront property like anywhere in the USA right now for $300,000, I'd be like, buy it. I mean, I don't know. Maybe don't buy it because it's a little scary if the price is that. I mean, it's good. I'd love it. I'd love to get some waterfront property for that price, but what's wrong with this? Is Jason Voorhees about to come out of that water? What's going on here? I am 90% confident the true difference is that since it's positive that waterfront property is worth more, it kind of makes sense. I'm 90% confident that the true difference in them is that waterfront is on average more than non-waterfront. So it's going to be this one right here, it looks like. And we just get the lower and the upper. 6, 4, 3, 4, 7, just because I'm being rude, my Pearson. 1, 3, 1, 8, 1, 4, seeing if you accept it and you have a margin of error. The questions have a little give on them. Yes, you do square the S's. Good stuff right there, Dylan. Yeah, the biggest thing for these is it's really just being very careful with the math. It's really just very, very careful when you plug in the numbers. I gave credit to someone yesterday because they showed me all the work they had written down by hand. They were in office hours, and we gave credit because it was like, I was like, you did everything right. And then they're like, I didn't. I think they forgot to square root it. Yeah, exactly. Check all your math. S1 squared over N1, S2 squared over N2 times the T. Make sure to calculate your T properly. If it's close to mine, like 90% with about 100 degrees of freedom, it'll be close to that. And there's a little bit of give on the questions. This is a nicer one on right or wrong. But yeah, we should do the serial question. Everyone gets stuck on that one. Everyone's like, how in the world? That doesn't require jump. It's just way easier with jump. So we'll do the serial one. Oh, man. Oh, he's right about here. I'm not even kidding. It was the first one I clicked. Too funny. First one I clicked. First problem I clicked. So with this question, this is not that tough. And I'll show you why. The reason it's not tough is we have jump. I was going to do it really quick, but let me slow it down because I'll have to do it again. You want to copy the data. Copy to clipboard. Now hit Control-C or Command-C. Now go over to jump. Inside of jump, you want to go to File, New, Data Table. Do not click inside of it when you do this. If you did, just X out and go to another one. It causes problems when you go to Edit, Paste with column names. You must paste with column names. If you hit Control-V, it won't do it. There is a shortcut for it, though. But go ahead and edit paste with column names, and you'll notice it's appearing there. If it looks like that, that's incorrect, and that's how some errors can occur. This is wrong and will not work for doing this problem. So now, we're going to make sure we have it as two quantitative vectors. And now we're going to go to Tables, Stack. So you should have two quantitative vectors, blue and blue. Stack, Stack. Click OK. Now we have the label of the cereal, and we have the sugar. If you want, double-click sugar or data, and let's say right here, sugar. Let's remove that. You double-click, go back, sure, sugar. And now we're going to do the analysis. To do the analysis, go to Analyze, Fit Y by X. With Analyze Fit Y by X, you're going to put label as the explanatory variable and sugar as the Y variable. This is just like we were talking about today when we make side-by-side box plots. There's a categorical X and quantitative Y. Very important right there to see that whenever we do these analyses, we're using a categorical X, like freshman or junior, 2 groups, and a quantitative Y, like social media friends. So now that we have the quantitative Y and the categorical X, we hit OK. We can get the side-by-side box plots by going here and doing quantiles. We don't have to do this, but it's nice. So now let's go ahead and do the 2-sample t-test by going to t-test. Here we are with our 2-sample t-test, and what do we get? A confidence interval. It did all the work for us. So I want you to think about this. If this interval goes from about 32 to 40, I'm just rounding it, what is the estimate of the difference? So if the interval goes from 32 to 40, what is the estimate of the difference? I mean, it's on the screen. If the interval goes from 32 to 40, what is the estimate of the difference? It's not exactly 32. It is like close to 32. That's the lower. And 40. And we can do our little thing we did way earlier. 32 is the lower estimate. 40 is the upper estimate. So what's the best estimate? The center of the interval. What is the margin of error of this interval? The margin of error is half the length of the interval. So what's the margin of error? Be careful, it's half the length. The center is the best guess. Because you can rewrite the interval as 36. Who knows the margin of error? What is the margin of error? Nice job. Great job, Darius. 4. There we go. Check this out. This is y bar 1 minus y bar 2. This is the standard error of the difference. If you divide these numbers, you get the t ratio. So 36 divided by 2 is basically 18, but it's not quite 2. Once again, you're just taking literally these numbers right here, dividing them to get the t. Nice job. Awesome. Yeah. I'll be there in just a little bit. We'll be finishing up here. But the interval is just listed below. No, Dylan. Maybe send me a message on it. It's all about those numbers getting right. Or send me a picture of your work. I'll try to take a look here. It's all, you have to get exactly the numbers. You got the confidence interval? Do it, cheat. Oh, no, all you need to do is you just need to go in and say that the waterfront costs more. So I am 90% confident that the waterfront costs more than the non-waterfront by the lower to the upper bound of the interval. So if you got the confidence interval, I am blank percent the 90% confident, or whatever it is, that the waterfront costs more than the non-waterfront by lower to upper. Make sure you click the more and then put in the lower bound to the upper bound. Don't do like that -1 that I did. I was just showing that it has a margin of error that it will give you. We've got the serial question done because the dollar amount was different. What? Oh, wow. This right here, we are literally just taking these values right here, 40.307. So 40.31, the lower bound of 31.58. And it's quite obvious that the children's cereal has way more sugar than the adult. Has way more sugar. 31.58 to 40.31 more sugar. A lot more sugar. Trying to think what else we have on here that we haven't done. Like, do research collected. Researchers collected. No, probably head off. Researchers collected. So researchers collected some samples right here. What is the null hypothesis? The null always has the equal sign. That makes this a joke. Joke. We're stating that there is no difference between a medium and small substrate and the pH level seen. Looks like there might be differences. Yeah, their p-value comes back. There is a difference. What did they have to assume right here? They have to assume that they are independent and the means are independent and the data is nearly normal. I hope they passed all those. They should really look at those in depth. Random, 10%. pause because now we have to think, what data are we working with? Quantitative data. So we're working with the nearly normal for the third condition, not success failure. And the fourth condition is independent groups, which means the small or large, whatever these are, substrates are not going to impact the means of the other groups. What conclusion you draw? I reject the null with a ridiculous amount of evidence. So we definitely reject the null. There is evidence for alternative. That should do it right there. P-value extremely low, reject the null. And you could find the exact p-value if you wanted. You could go right here, a t-statistic of 16.3, and they were testing to see, I think they were testing to see if it's not equal to 0. So you would go here, and you would enter in your degrees of freedom. There's 149 degrees of freedom. We are going to find the p-value using t. We are doing the outside test right there, and the t-statistic is 16.33. So we have to enter in the negative version of that, and 16.33 as the positive version of that. And this has, yeah, this is so, oh, we're doing the between, we need to do outside. There it is. We actually just stumbled upon it. That's the p-value. It's 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 Kind of. Well, remember, it's the 2-sample t. Kind of. Well, remember, it's the 2-sample t. Really good answer right there. It's the 2-sample t. If it was the 1-sample t, that would be correct. It means definitely a larger sample sizes, and it would be something related to the total sample size. So probably they had at least like 151 sample size, because the 1-sample t is n-1, the 2-sample t is too complicated. Really good answer right there, Dylan. I like that. Yeah. So they got some pretty large sample sizes here. They don't tell you the n1, the n2. Explain what the, I gotta mark this real quick. Dylan, great answers. Yeah, because that's the 1-sample t. So you'd been totally right if it was a 1-sample t. That means they tested the mean and they took this many samples. But this is a 2-sample t, so they probably have a decent sample size if they have that many degrees of freedom. Standard deviation comes into play, but I think that you could say that they had at least 151, because the maximum's n-2, so they got at least 151 total sample size. We wouldn't ask that deep of a theoretical question, though, but that's a really good, like, I'm glad you followed up with that. The 2-sample t has a too complicated degrees of freedom formula. The 1-sample t is n-1. Okay, explain the context of the p-value. Well, what we saw, the differences we saw were very likely by random chance. So there is this chance of seeing a difference in this mean score this larger by simple, that sounds right. Ooh, okay, let's check out some other. This one looks wrong. It's probably gonna be this one just by virtue of how questions, permutate a right answer with a wrong answer variant. If I was taking the SAT, I would just click on that one automatically because it's got elements of both. If the mean score memories for you people are not taking, if the mean memory score for people taking ginkgo biloba and people not taking it are the same. Okay, they should have done that. Okay, it's better. It's saying if the null is true, because the p-value is the probability of our results or results from our stream, which this covers, by random chance variation, given the null is true. So this is given the null is true, here's the probability of our results or something more extreme due to random chance variation. That's what a p-value is. So it is B. And we just simply did it by virtue of, I bet it's this one because it has the elements of the other two. Come on, trick us. Make it harder. State your conclusion about the effectiveness of ginkgo biloba. Well, we didn't observe a difference. The difference we saw was likely by random chance. Since the p-value is high, there is no evidence. So there it is right there. There's no evidence of a difference. So whatever they're going to say after that, we don't have evidence of a difference. We don't reject the null because the p-value is high. Just let the null fly. What kind of error could we have made? So if it actually does work, remember, we didn't reject the null. So in a type 1 error, the null is true and you reject it. That would be saying this medicine works and it actually doesn't. In a type 2 error, the null is false and we fail to reject it. So we don't know if we made a type 2 error, but the only error we could have made is a type 2 because we didn't reject the null. But if the null is false, like we should have rejected it, we did make a type 2. So insist that it works. What type of error do they claim you made in your conclusion? There we go. Good stuff. Drinking glass 1. I guess we could end with this one because this one's, we've done confidence intervals by hand. We haven't done a test by hand. So this kind of covers all the bases of what these questions cover to do a confidence interval by hand. So let's do this one right here, which is a test by hand. So we have not done the test by hand yet. Okay, so the null hypothesis would be that there's no difference between how much people pour in a nice job, this perfect moment for this. Remember, the null has the equal sign. The null has the equal sign. So the mean for the two glasses is the same as the null, which we throw in the equal sign. Mu1 minus mu2 equals 0, mu2. Thing of our channel. Now, are they looking for a difference? Let's see right here. Researchers investigated how much you pour in a soda glass. I think they're just seeing if there's a difference. They don't tell us if we're looking for a greater or less than. It's just a difference. There you go. Then we test to see if it's different, and we'd use the does not equals two-tailed test. So now you have to go and take the table, and thank you, Dylan, good practice. It all boils down to notation. It just becomes a notation question from here. So we should also check that these are random people. This is less than 10% of the total population. The data is nearly normal, and both means are independent. Like, people aren't changing how much they get based on their glass size of the other glass size. Okay, so with this right here, we're going to do y bar. It's going to be PQS. It's going to be small minus y bar large. There's a chance I could have reversed that, but usually it does reverse alphabetical order, LMNO PQRS. Yep. Usually it does reverse alphabetical. You put the S first because it's last. I don't know why, but that's usually how problems solve. That also works for the Walmart Target. I believe if you do this, you should get it right when you do Walmart Target problems, if you have to solve them. And please, if you get it wrong because of that, let me know. Yeah, do they not tell us in this problem? They should. Wait, they should say it right here. Mu2 is the small. Oh, no. Dylan, we're about to do it wrong. 5,000 points, Dylan. Mu2 is the small. So large, small. So it is saying mu2 is the small. Yep, mu1 minus mu2. Or y bar 1 minus y bar 2. Yeah, which we assume in the problem that y bar, they should have just written y bar large minus y bar small equals 0. And the alternative hypothesis, y bar large minus y bar small not equal to 0. And then we just go here, square roots, s sub large squared over n sub large plus s sub small squared over n sub small equals t with complicated degrees of freedom. Okay, plug in the numbers. The glasses large minus small is 6.31 minus 5.09 equals to, we're going to run out of room. Beep. That is equal to 1.22. And the bottom of the equation is going to be 1.86 squared over 22. And then 29 on this one, and 2.83 squared. Okay. And we solve the standard error on the bottom. Standard error is the bottom of the equation. So 1.86 squared divided by 22. 2.83 squared divided by 29. Add them up. Square root them. 0.658. Okay. Oh, that's going to be a t-statistic of about 1.8 or so. And 1.22 divided by that, 1.85. There's the t. So now we use the t to find the p-value. And the p-value is going to be something close to 0.064. And are we using the classic alpha? I do not reject the null. The data do not provide sufficient evidence that they are different. Now, I might get this one wrong. Let's see if I got it right. I got it wrong. Very close to the right answer on this. There we go. It was the third decimal place that got me. Let's see how we get that p-value. To get the p-value, we have to go to the t-curve. To get the p-value, you have to, or you can guess at it. It was very close to the classic 95% confidence interval 1.96. That's how I guessed at it, if you're wondering. But we're going to go here to the t-applet. Now, the first thing you have to do on the t-applet is get the degrees of freedom. To calculate the degrees of freedom, we need both standard deviations in both sample sizes, 1.86, 2.83. So 1.86. And that was 22, I think. 2.83. 29. Let's double check our work. And we have the right, I think, everything. So it's 48.15, which tells us the shape. And we're going to find the p-value using the t. We are doing the outside test because the does not equals test was performed. We go back to our calculator and take our t-statistic, plug in the negative version of it and the positive version of it. And it looks like I got lucky on the rounding. It's basically 7%. I should just get 7%, which is higher, but I got close enough to the answer that I was like, sure, why not? But it's basically 7%. That's got it. That is, there you go. It should have been about 7%. It's probably 7% plus or minus 2. So if we enter in that, it's going to say wrong. And is it plus or minus 0.003 or 0.002? Oh, it's 0.003. No way. So what was my first guess again? Ooh. I think I guess 0.064, right? Yeah. There's the boundary of it. Yep. But we reject the null because it's higher. It'd be funny if it was like very close to 0.05 and you could like mess with it and make it above or below, and then that would mess with the answer. I wonder if any of the variants turn out that way. Well, that's got it. I think we're good. Is it 1x the t value? Are you saying, Dylan, for when you put it into the applet, make sure you do the negative and the positive, and then make sure you have the right degrees of freedom, and you're doing the outside test right now, and then it's just the p-value right here. Does that make sense? So you just take the t statistic and plug it into the applet and graph it. And negative and positive of the t. Whatever t... Oh, that was a door. So whatever the t is, you put it negative and positive right here. And I carried all the decimals. It'd be a little different if we... It's not really that different. So tired. 8.07. So take the negative and positive t, plug it in right there. Like negative t, positive t. Because the two-tailed test, if this was a less than test, we would graph below where we landed. If this was a greater than test, we'd graph above where we landed. If it's a does not equals test, we graph outside, which now it's messed up, but we graph outside right there. So that's the does not equals test. That's the negative test. That's the greater than test. With that, we're going to head on off. Going to go to in-person office hours. Bye for now, everyone. Bye.